Good morning, guys. I hope everyone's having a good day. This is your warm-up for today, so let's start here. Get your notebooks out and complete the warm-up, and this is going to go back a little bit to the HR diagram, so it should be very easy for you. So looking at the diagram that you see on the screen, it says compare Betelgeuse to the sun. It says use complete sentences and compare the two stars in as many ways as you can. So there should be more than one sentence on your paper because there are several categories that you can use. So Betelgeuse is here, the sun is here, but you should know that part. So you can pause the video here, and when you come back, we can go over your answers. And remember what I said, everyone should be putting this in their notebook right now, or on a piece of paper, or on the back of a worksheet. So, comparing Betelgeuse to the sun, we can clearly see a couple of things. The sun is a main sequence star, and Betelgeuse is a supergiant. So there's one comparison. Betelgeuse is in spectral class M, and the sun is in spectral class G. The sun is a yellow star, and Betelgeuse is a red star. Betelgeuse is a larger star than the sun. The sun is a hotter star than Betelgeuse. The sun is about, between 5,000 and 6,000 degrees, and Betelgeuse is about between 25 and 3,000 degrees. Betelgeuse is a lot brighter, or has a greater luminosity than the sun, because you can see it's higher on the chart. And I'm trying to think if we missed anything, but I don't think so. So you should have at least a few of those things written on your paper. Now, if you have any questions, I need you to hold on to them and ask me the next day to make sure that you're clear on HR diagram, because it will be on your 6 weeks test. If you have field trip money or your course selection forms, please hold on to them until tomorrow when I'm back. Okay, keep them one extra day so that they're in a safe place and I can take them up from you when I'm here. And we're going to move on to today's activity. The first thing we're going to do is we're going to watch a video. Today's topic is covering the electromagnetic spectrum in review, but we're also going to start talking about something called red and blue shift and the Doppler effect. So we're going to watch this video, and then it's going to lead us into our activity. So during this video, I would like you to watch carefully, listen to the details, and jot down anything important you think you might need for later on in the lesson.
Most scientists believe that our universe is expanding. That belief is based on an interesting property of light waves called the Doppler effect. Here's how it works. All waves travel outward from a source. A stone dropped in a pond, for instance, will produce waves that move out in a circular pattern from the splash. Light works the same way. When a camera flashes, light waves move out from the flash bulb. When the source of a wave is stationary, the waves can be thought to form circles radiating out from the source. But when the source is moving, something very interesting happens. The waves ahead of the moving source are bunched closer together. The waves trailing behind the moving source are spread out.
We hear this effect when a moving car blows its horn as it passes us. Hear a high-pitched sound as the car approaches us because the motion of the car bunches the sound waves closer together. When the car passes us, we hear a distinct drop in pitch because the sound waves are now spread out by the car.
Light waves show a similar shift. If a source of light, like a star or a galaxy, is moving toward us, the light waves are bunched together, and we see the light with a slight bluish tint. If the star or galaxy is moving away from us, the waves are stretched out, and we see a reddish shift in the color. Because all galaxies show a red shift in the color of their light, this is evidence that they're moving away from one another. So the red shift is evidence that our universe is expanding.
So that video may have been a little bit hard to hear, but what it's talking about is what is happening to light waves, which is forming the red and the blue shift. So I'm going to explain what that is in just a minute. So I just want to review, before I do that, what we've been talking about. Here is the entire electromagnetic spectrum, going from largest wavelength, radio, to smallest wavelength, gamma. And what we're going to be focusing on today is visible light, which is, you know, the only waves that we can see. And visible light is when white light is split and you can see all of the colors of the rainbow. But now there's something specific you need to know about the wavelengths of those light, the visible light. So you may want to write some of this down. But here are the colors of the rainbow that make up the parts of visible light that we can see. And here's what their wavelengths look like. So we have red, orange, yellow, green, blue, indigo, and violet. And as you may notice, the wavelengths start out very large and they start to get smaller as you get towards the end of the rainbow. So red has the largest wavelength, similar to when we talk about radio waves, and violet has the smallest wavelength. And remember, this is only visible light, which is just one part of the electromagnetic spectrum. So as we go down, the colors will have a smaller and smaller wavelength. Now, starting to talk more about redshift like was seen in the video. If we are looking at something with our eyes, studying it, like a star or an entire galaxy, this is what redshift says. And I would prefer that you write down everything that is underlined. So you'd start by writing redshift and then the definition. So galaxies are moving away from each other. This is what scientists have found because of redshift and what redshift shows them. So when a star or a galaxy is moving away from our view, the light's wavelength, the light that it's given off, appear elongated. Elongated means they get longer or they appear to stretch. So when a galaxy or a star is moving away from the Earth, the wavelengths of light are shifted to the red end of the spectrum. And I'm going to go back up here for a minute. The red end of the spectrum means that it's shifting to the red end of the rainbow. And as you can see, the red end of the rainbow has the longest wavelengths. So when it stretches out, they appear, or when it appears to stretch out, it looks red, because that is the part of the rainbow that has the longest wavelengths. So that's why we call it a redshift. It appears red. The wavelengths are stretching out. We can tell that the object is moving away from us. Now, blue shift is just the opposite. Blue shift means that galaxies or stars or other objects that scientists are studying are moving toward the Earth. And we know this is happening because the wavelengths are getting shorter instead of longer, which means it's moving to the blue end of the spectrum, or the blue purplish end of the rainbow. And remember, going back up here again real fast, that the purple end of the spectrum has the shortest wavelength. So when they start to get shorter like that, we know that that's a blue shift. So it's kind of squishing the wavelengths closer together, and we know that that object is moving closer to us rather than moving further away. So we call that blue shift. So there's redshift and there's blue shift, and they are total opposites of each other. So I kind of want to compare this to a slinky. When you have a slinky and you're not using it, it's unstretched. It's sitting there, all the coils are very tightly together, and that's what is happening when you experience a blue shift. When something moves towards you, all of the wavelengths are compacted or they're tight together, which means that that object is moving towards you. However, when you let a slinky drop to the floor and that end of the slinky is moving away from you, it stretches. So when a galaxy or a star is moving away from you, in your eyes, it's stretching the wavelengths, meaning it's stretching the wavelengths, making them longer, moving toward the red end of the spectrum that has the longer wavelengths. So this would be something that's showing more of a red shift, And since these are closer together, it's showing more of a blue shift, if that comparison makes sense to you. This is an example of spectral lines and how scientists can actually see if something is red shifting or blue shifting. So up here would be the original sample, and you all have seen spectral lines before now. You need to think about gas tubes. This is the regular sample of a star or a galaxy's elements without moving at all. Now redshift means, if you can tell, if you see this series of 3 lines is now moved very slightly to the right. Same with all of these lines up here. They have shifted very slightly to the right. And if you look at the right, that is the red end of the spectrum, or the red wavelength. So the waves would have appeared to stretch out. Here you can see that it's actually moving toward the color red. So that would be a red shift. That would mean that this object, galaxy, star, whatever it might be, is moving away from us. However, if you go back to the original and compare it to the one down here, these spectral lines and these spectral lines and all of these up here have shifted slightly to the left. And going to the left means it's moving to the blue-purple end of the spectrum, which means that is a blue shift. The wavelengths are actually getting more tightly packed together. So that means if it went from here to here, that object is actually moving closer to us. This is another example. So here's the sample. The object is at rest. A blue shift means that they're moving slightly to the left again towards the blue end of the spectrum. If you compare it to the one down here, they're moving slightly to the right toward the red end of the spectrum. The last thing I want you to do is to think about the video. Think about what I just told you. Think about the notes that you wrote down, and hopefully you did. Is complete the sentences by writing them in your notebook. And then I'm going to give you the answers. So number 1, red shift is when a galaxy or another object is moving blank the Earth. Number 2, blue shift is when a galaxy or another object is moving blank the Earth. Number 3, during a blue shift, the wavelengths of light get, fill in the blank. And number 4, during a red shift, the wavelengths of light get. And last, number 5, blank is the color with the longest wavelength. So I want you to write all of these sentences in your notebook. I want you to complete them with the word that you think goes in the blank. You can pause the video here, and then I will go over what should be in the blank, and I need you to correct that along with me. Okay, hopefully everyone has 5 sentences in their notebook right now. Very important. All right, number 1, red shift is when a galaxy or another object is moving away from the Earth. So remember, blue shift is the opposite. Blue shift is when a galaxy or another object is moving towards the Earth. So what I'm typing is what should go into the blank right now. Number 3, during a blue shift, the wavelengths of light get shorter. And during a red shift, the wavelengths of light get longer. And you can also say longer, stretched out, shorter, or more compressed. That's fine. And number 5, red is the color with the longest wavelength. Okay, this is the last thing you are doing today, and this is the only thing you are turning in for a grade. And it should be an easy 100, so please make sure that you are working and on task at all times. You are sending a message to Proxima Centauri, which is the next nearest star to the Sun. All you have to do is put a check mark in whatever box, whatever kind of wave you would like to send the message on. You may use websites, these, or whichever ones you choose to research how to find all the information, and then you will fill out the page below. What kind of wave did you choose from up above? Why did you choose that kind of wave? What is your message going to say? And it doesn't have to be anything extensive or long. Okay, how far is it going? And I already kind of mentioned that with how far away that star was. What kind of speed is it going to use? How long will it take to get there? And so if you send it, on today's date, when is it going to arrive? And think about how many light years away it is. So again, you may research to find your information, but this needs to be completed and turned in before you leave. Have a great day.